The universe is filled with unbelievable sights. There are stars that dwarf our Sun, planets that are as massive as small stars, and black holes so large that a galaxy full of stars revolves around them. In this cosmic arena, colossal giants challenge what we thought was possible in terms of scale in this universe. And if you've ever felt uneasy at the thought of endless expanses and towering entities, these immense wonders might just send a shiver down your spine. So, buckle up as we explore these awe-inspiring behemoths one by one.
Wasp-17b, the puffy exoplanet defying expectations. Unlike any planet in our solar system, Wasp-17b is both enormous and incredibly lightweight for its size. This gas giant is nearly twice the diameter of Jupiter, but has only about half its mass, making it one of the least dense planets ever discovered. Scientists describe it as a puffy planet because it appears to have an atmosphere that is expanded far beyond what is typical for a gas giant. Located about 1,300 light-years away in the constellation Scorpius, Wasp-17b was first discovered in 2009 as part of the Wide-Angle Search for Planets, or WASP, project. The method used to find it was the transit method, which involves detecting tiny dips in a star's brightness when a planet passes in front of it. As Wasp-17b crossed in front of its host star, astronomers noticed that the dimming pattern suggested a planet much larger than expected for its mass. This raised immediate questions about how such a world could exist. Planets are generally expected to have a certain density based on their size and mass. The larger the planet, the more mass it should have to hold itself together under the force of gravity. Wasp-17b's low density suggests that its atmosphere is extremely extended, making it look bigger than its actual core. This inflation effect is still not fully understood, but astronomers suspect that its extreme proximity to its star plays a major role. Wasp-17b orbits very close to its parent star, completing a full orbit in just 3.7 days. This means it is subjected to intense radiation, which superheats its atmosphere and causes it to expand. The temperatures on Wasp-17b are estimated to be well over 1,500 degrees Celsius, hot enough to melt many metals. This heat energy could be preventing the planet from contracting into a denser form, making it appear much larger than it otherwise would be. The same heating process may also be gradually stripping away its outer layers, with some of its atmosphere likely being lost into space. Unlike most planets, which orbit in the same direction that their stars rotate, Wasp-17b moves in the opposite direction. This is known as a retrograde orbit and is extremely rare. Scientists believe that something must have happened in the planet's past to cause this unusual motion. One possible explanation is that Wasp-17b experienced a close encounter with another massive planet in the system, which could have altered its orbit through gravitational interactions. Another theory is that a powerful force from the star itself reversed its motion at some point in its history. Most gas giants are expected to have relatively compact atmospheres compared to their cores, but Wasp-17b is different. One theory is that the intense radiation from its star has injected so much heat into its outer layers that it has caused the planet to expand beyond normal limits. Another possibility is that Wasp-17b formed in a way that made it naturally less dense, perhaps by accumulating more lightweight gases like hydrogen and helium than heavy elements. Some scientists suggest that additional forces, such as strong winds or tidal effects from its star, could be playing a role in keeping its atmosphere inflated. By studying how light from its star filters through the planet's outer layers, scientists can determine what elements are present. Early observations suggest that Wasp-17b's atmosphere may contain clouds or hazes that influence how light passes through it. Learning more about its atmospheric composition can help researchers understand the chemistry of distant worlds and how they evolve under extreme conditions. Jupiter is much denser than Wasp-17b despite both being gas giants. This suggests that gas giants can take many different forms depending on factors such as their distance from their star, their temperature, and the way they formed. Some exoplanets are far hotter than anything seen before. Some are much colder than expected, and some, like Wasp-17b, are so puffy that they almost seem impossible. Studying planets like Wasp-17b helps astronomers refine their theories about planetary formation and evolution. Traditionally, it was believed that planets formed in a relatively predictable way, with gas giants being dense and compact due to the intense gravity needed to hold onto their atmospheres. But Wasp-17b shows that this is not always the case. Since its discovery, other puffy planets have been found, but Wasp-17b remains one of the most extreme examples. SN 1987a, a supernova that reshaped our cosmic understanding. When it erupted in 1987, SN 1987a provided astronomers with their first chance to study a supernova in modern detail. It was not just another distant explosion in an unknown galaxy. It was close enough, by cosmic standards, for scientists to collect data that would change our understanding of how stars die and what happens in the aftermath of their destruction. Located in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, SN 1987a was the closest observed supernova since the invention of the telescope. At just 168,000 light-years away, it gave astronomers an unprecedented opportunity to study the death of a massive star. Unlike supernovae in far-off galaxies which appear as faint points of light, SN 1987a was bright enough for its structure and evolution to be tracked in real time. The star that exploded was a blue supergiant named Sandelik-69202. Before the explosion, this star was more than 18 times the mass of the Sun and had already gone through millions of years of fusion, converting hydrogen into heavier elements. The explosion itself occurred when the core of the star ran out of fuel and collapsed under its own gravity. This triggered a powerful shock wave that tore through the outer layers, releasing an enormous amount of energy in a matter of seconds. One of the most groundbreaking discoveries from SN 1987a came from the detection of neutrinos. These tiny, nearly massless particles are produced in vast quantities during a supernova, but they interact so weakly with matter that they are nearly impossible to detect. However, just before the visible explosion was recorded, underground detectors on Earth picked up a burst of neutrinos, confirming long-standing theories that neutrino production plays a critical role in stellar explosions. This was the first direct evidence linking neutrinos to a supernova event, solidifying their place in our models of how stars collapse. Before its discovery, scientists believed that red supergiants were the primary candidates for core collapse supernovae. These stars are massive, cool, and unstable, making them prime candidates for explosive deaths. But Sandelik was a blue supergiant, a much hotter and more compact star than expected. This forced astronomers to reconsider how stars evolve before they explode, leading to new theories about the late stages of massive stars. In the years following the explosion, telescopes continued to observe SN 1987a's aftermath. The debris left behind expanded outward, forming an intricate structure of glowing rings and shock waves. One of the most striking features was a set of 3 rings of gas surrounding the explosion site. These rings had likely been expelled from the star thousands of years before the explosion, possibly due to interactions with a companion star or dramatic mass loss events. When the blast wave from the supernova hit these rings, they lit up, creating a glowing outline of the material the star had shed in its final millennia. The outer shell of debris from SN 1987a continues to expand. As it moves outward, it slams into surrounding gas, heating it up and causing it to glow in X-ray and radio wavelengths. This provides an opportunity to study how supernova remnants evolve over time, giving astronomers insight into the long-term impact of such explosions on their surrounding environment. When a massive star collapses, its core can become either a neutron star or, if it is massive enough, a black hole. The conditions inside a newly formed neutron star are extreme, densities so high that protons and electrons are crushed together, forming a sea of neutrons packed into an incredibly small space. For decades, scientists have searched for signs of a neutron star at the heart of SN 1987A's remnant. Recent observations suggest that a dense, compact object does appear to be hiding within the expanding cloud of debris. Observations also showed that significant amounts of dust were forming within the cooling debris of the explosion. This challenged previous ideas that supernovae primarily destroyed dust rather than created it. Instead, SN 1987A demonstrated that these explosions could be major contributors to the dust found in galaxies. Over the years, SN 1987A has provided insight into the physics of core collapse supernovae, the behavior of high-energy particles, and the long-term evolution of stellar remnants. New observations, especially with instruments like the James Webb Space Telescope, continue to reveal fresh details about its expanding shockwave, its effect on the surrounding gas, and the fate of its collapsed core. By comparing its explosion to other known supernovae, astronomers have refined their models of how stars evolve, how they lose mass before exploding, and how the elements they create are distributed. Because SN 1987A was so close and well studied, it has become a benchmark for interpreting more distant and ancient supernovae. When astronomers detect supernovae in distant galaxies, they use SN 1987A as a reference point to estimate the properties of those explosions. Its influence extends beyond just its own event, shaping how we understand similar cosmic phenomena across the universe. As technology advances, researchers continue to find new ways to extract information from the data collected on SN 1987A. Some of the most powerful telescopes, including those that can observe in infrared and X-ray wavelengths, are being used to study the ongoing changes in the expanding supernova remnant. With each new observation, astronomers refine their understanding of how massive stars die and what happens in the aftermath of their destruction. Jupiter, the gas giant that sets a cosmic benchmark. In our own backyard, Jupiter is the largest planet of the solar system, a massive world that dominates the region beyond the asteroid belt. It is a gas giant, meaning it has no solid surface and is made mostly of hydrogen and helium, much like the Sun. Its enormous size and influence make it one of the most important celestial bodies in our solar system. Jupiter serves as a benchmark, a standard against which other gas giants, both within our solar system and beyond, are measured. Jupiter's scale is almost difficult to comprehend. With a diameter of approximately 143,000 kilometers, it is so large that more than 1,300 Earths could fit inside it. Its mass is more than 300 times that of Earth, making it the most dominant entity in the solar system after the Sun itself. Had Jupiter been about 80 times more massive, it could have ignited nuclear fusion and become a star rather than a planet. This is why some scientists consider Jupiter a failed star, though it lacks the necessary conditions to truly be one. Even as a planet, it has shaped the evolution of the solar system in profound ways. In our own solar system, Saturn, Uranus, and Neptune are also considered gas giants, or in the case of Uranus and Neptune, ice giants due to their different compositions. However, Jupiter sets the standard. It is the first example of a truly massive planet, and astronomers use it as a measuring stick when comparing newly discovered exoplanets, planets outside our solar system. When scientists find gas giants orbiting distant stars, they describe them in terms of their size and mass relative to Jupiter. Some of these exoplanets, known as hot Jupiters, are similar in size but orbit much closer to their stars, creating extreme conditions with scorching temperatures. Others, called super Jupiters, are even more massive, stretching the limits of what can be considered a planet versus a failed star. One of Jupiter's most distinctive features is its thick, turbulent atmosphere. It is covered in swirling clouds of ammonia and water, stretched into bands of color by strong winds that reach speeds of up to 600 kilometers per hour. These bands create Jupiter's iconic striped appearance, with lighter zones and darker belts flowing parallel to the equator. Powerful jet streams keep these bands moving in opposite directions, creating immense storms where they meet. The most famous of these storms is the Great Red Spot, a swirling, high-pressure system that has raged for centuries. This enormous storm is so large that it could swallow Earth whole, and it has been observed continuously for at least 200 years. Though it has been shrinking in recent decades, the Great Red Spot remains a defining feature of Jupiter, an indicator of the planet's extreme and dynamic weather. Smaller storms also rage across Jupiter's surface, some of them merging or dissipating over time. These storms provide valuable insight into how planetary atmospheres work, offering a way to study atmospheric physics on a grand scale. Beneath Jupiter's swirling clouds, the planet's interior remains mysterious. Without a solid surface, Jupiter's gaseous atmosphere extends downward, gradually transitioning into a dense, hot interior. As one descends into the planet, the immense pressure causes hydrogen gas to transform into a strange state called metallic hydrogen. This exotic material is believed to behave like a metal, conducting electricity and generating Jupiter's powerful magnetic field. Jupiter's magnetic field is one of the strongest in the solar system, stretching millions of kilometers into space and creating intense radiation belts around the planet. These radiation belts are so extreme that they pose a significant challenge to spacecraft, requiring special shielding to prevent damage from high-energy particles. Scientists believe that deep within the planet lies a dense core of rock and metal, surrounded by a thick layer of metallic hydrogen. However, this core is still not well understood. Some models suggest that Jupiter's core may be partially dissolved, blurring the distinction between solid and liquid. Others propose that it is more compact and stable, though hidden beneath thousands of kilometers of crushing pressure. Understanding Jupiter's core is crucial for understanding how gas giants form, both in our solar system and around other stars. Jupiter's massive gravitational influence extends far beyond the planet itself. It has at least 95 known moons, ranging from small, irregularly shaped rocks to enormous worlds that rival planets in size and complexity. The four largest, known as the Galilean moons, Io, Europa, Ganymede, and Callisto, were first observed by Galileo Galilei in 1610. Each of these moons is unique, offering its own mysteries and scientific intrigue. Io, for example, is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly reshaping its surface. Europa, on the other hand, is covered in a thick shell of ice, beneath which scientists believe an ocean of liquid water exists. This ocean, kept warm by tidal forces from Jupiter's gravity, is one of the most promising places in the solar system to search for extraterrestrial life. Ganymede, the largest moon in the solar system, is even bigger than Mercury and has its own magnetic field. Callisto, heavily cratered and ancient, offers a glimpse into the early history of the solar system. Jupiter's role in shaping the solar system cannot be overstated. Its immense gravity has influenced the orbits of countless asteroids and comets, sometimes acting as a protector by deflecting dangerous objects away from Earth, and other times sending them toward the inner solar system. Some theories suggest that Jupiter helped clear out debris during the early formation of the solar system, preventing the development of additional planets beyond Mars. Others argue that its gravity may have disrupted the formation of a potential super-Earth in the inner solar system, changing the course of planetary evolution. Spacecraft like NASA's Juno mission have revealed new details about the planet's atmosphere, magnetic field, and deep interior. Juno's close flybys have captured stunning images of Jupiter's poles, showing swirling cyclones unlike anything seen elsewhere in the solar system. Future missions, including those targeting Jupiter's moons, aim to uncover even more about this giant world and its place in the cosmic puzzle. The Sun, our local beacon of stellar immensity, The Sun is the heart of our solar system, a massive sphere of glowing plasma that provides the light and heat necessary for life on Earth. It is a constant presence in the sky, rising and setting each day, yet its true nature is far more extreme than what can be seen from the ground. The Sun is a powerful, dynamic object, a churning ball of nuclear reactions that fuels everything in our cosmic neighborhood. It is the reason planets orbit, the source of energy for plants and animals, and the force that shapes the very structure of our solar system. With a diameter of about 1.4 million kilometers, the Sun is roughly 109 times wider than Earth. More than 1 million Earths could fit inside it, yet it is far from the largest star in the universe. There are stars out there hundreds, even thousands of times bigger. But for us, the Sun is the ultimate reference point for understanding stellar power and size. It is classified as a G-type main sequence star, or G-dwarf, a category that includes stars with moderate temperatures and lifespans. Though it may seem small compared to the most massive stars in the universe, it is still an immense and complex object. At its core, the Sun is a nuclear furnace where hydrogen atoms fuse together to form helium. This process, known as nuclear fusion, releases an enormous amount of energy. The core reaches temperatures of about 15 million degrees Celsius, an environment so extreme that atoms collide with enough force to overcome their natural repulsion and merge together. This energy slowly moves outward, first through a dense region called the radiative zone, where photons of light are absorbed and re-emitted countless times. It can take thousands of years for this energy to make its way to the next layer, the convective zone, where hot gases rise and cooler gases sink, creating a boiling motion that drives the surface activity of the Sun. The outermost layer, the photosphere, is the part of the Sun that we see from Earth. It shines brightly, with a surface temperature of about 5,500 degrees Celsius. Above this lies the chromosphere and the corona, layers of hot plasma that extend outward into space. The corona, which is much hotter than the Sun's surface, remains a mystery to scientists. It is visible during solar eclipses as a faint halo of light surrounding the darkened Sun. This outer region constantly streams charged particles into space in the form of the solar wind, a flow of energy and matter that reaches all the planets, influencing their atmospheres and magnetic fields. Despite its steady presence in the sky, the Sun is not a quiet or unchanging object. It experiences an 11-year cycle of increased and decreased activity, marked by the appearance of sunspots, dark patches on its surface caused by magnetic disturbances. These sunspots can be larger than Earth and are often linked to powerful eruptions such as solar flares and coronal mass ejections. These events send bursts of charged particles into space, sometimes reaching Earth and causing disruptions to satellites, communication systems, and even power grids. The auroras, known as the northern and southern lights, are caused by these particles interacting with Earth's magnetic field, producing dazzling displays of light in the polar skies. The Sun's gravity holds the solar system together, keeping planets, moons, asteroids, and comets in orbit. Without the Sun's stabilizing presence, the orbits of planets would drift and life as we know it would not be possible. Its light drives the water cycle, fuels photosynthesis, and provides the warmth necessary for liquid water to exist on Earth's surface. Yet despite its vital role, the Sun is only temporary. Like all stars, it has a finite lifespan. The Sun is about 4.6 billion years old and is currently in the middle of its life cycle. It has enough hydrogen fuel to continue shining for another 5 billion years. But eventually, it will begin to run out of fuel, and its core will start to contract while its outer layers expand. In this phase, the Sun will become a red giant, growing so large that it may engulf Mercury, Venus, and possibly even Earth. In this swollen state, it will shed its outer layers, creating a beautiful but short-lived planetary nebula, leaving behind a dense, hot remnant called a white dwarf. Although the Sun is not the largest star, it provides a crucial reference point for understanding stars across the universe. Astronomers measure the size and brightness of distant stars in relation to the Sun, describing them as larger or smaller, hotter or cooler. Red dwarfs, for example, are much smaller and cooler than the Sun, while blue giants are far hotter and more massive. Some stars, like the red supergiant Betelgeuse, are hundreds of times the Sun's size, while hypergiants such as Scudi stretch to unimaginable scales. Wasp-12b, a scorching hot Jupiter on the edge of obliteration. Wasp-12b is a gas giant orbiting so close to its star that it is being pulled apart by intense gravitational forces. The heat from its star is so extreme that it has changed the planet's structure, making it one of the most unusual worlds known to science. Located about 1,400 light-years from Earth in the constellation Auriga, Wasp-12b was discovered in 2008 using the transit method. As it passed in front of its star, scientists detected dramatic drops in the star's brightness, revealing a planet that was not only massive, but also incredibly close to its host star. It takes just 1.1 Earth days for Wasp-12b to complete one orbit, meaning it is almost brushing against the surface of its star. This tight orbit exposes the planet to extreme radiation, heating its atmosphere to over 2,500 degrees Celsius. The extreme heat has a powerful effect on Wasp-12b's atmosphere. At such high temperatures, molecules are torn apart, making it difficult for the planet to hold on to many of the elements found in cooler gas giants. The planet's atmosphere has expanded, stretching out like a teardrop due to the immense gravitational pull of its star. In fact, Wasp-12b is being stripped of its outer layers, and much of its atmosphere is being lost to space. This process, called atmospheric escape, is reshaping the planet, making it unlike anything seen in our solar system. Even among hot Jupiters, Wasp-12b is an extreme case. Most planets maintain a roughly spherical shape, but Wasp-12b is so close to its star that it is being stretched into an elongated egg-like form. This distortion is caused by tidal forces, the same type of gravitational interaction that creates ocean tides on Earth. However, in the case of Wasp-12b, the effect is so strong that the planet itself is being physically reshaped. One of the most striking discoveries about Wasp-12b is that it is one of the darkest planets ever observed. It absorbs more than 90% of the light that hits it, making it appear almost black. Most gas giants reflect at least some of the light from their stars, but Wasp-12b's thick atmosphere seems to trap light instead. Scientists believe this could be due to a lack of reflective clouds and the presence of molecules that absorb light instead of scattering it. The extreme heat could also be preventing cloud formation, leaving the planet with a dense, heat-trapping atmosphere. The fate of Wasp-12b is sealed. Scientists estimate that within a few million years it may be completely destroyed. As it continues to lose mass to its star, it will either shrink to a much smaller size or be torn apart entirely. This kind of planetary destruction is rare, but it provides valuable insight into how some planets interact with their stars over time. Studying Wasp-12b allows astronomers to witness the final stages of a planet's life, giving clues about what might happen to other close-orbiting exoplanets in the future. Despite its close orbit, it has existed long enough for astronomers to study its evolution. This suggests that some planets may be able to resist being completely torn apart for longer than expected. The planet's stretched shape, intense heat, and rapid mass loss make it an important case study for understanding how extreme exoplanets behave. In our solar system, the gas giants are far from the Sun, where it is cold enough for them to retain thick atmospheres. But Wasp-12b shows that gas giants can form or migrate to regions where the conditions seem impossible for their survival. This has led scientists to reconsider how planets form and move within their systems. Some theories suggest that Wasp-12b may have started farther from its star and then migrated inward due to gravitational interactions with other planets or the disk of material surrounding its star in its early years. Scientists have detected elements such as hydrogen, helium, and carbon-based molecules in its atmosphere. The presence of carbon-rich compounds suggests that the planet's chemistry is different from Jupiter's, which has more oxygen-rich compounds. Future observations of Wasp-17b could reveal more about the specific gases present in its atmosphere, how they interact with heat and radiation, and what ultimately happens as the planet continues to lose mass. While Earth is a stable, life-supporting planet, many exoplanets exist in far more chaotic and dangerous environments. By studying extreme cases like Wasp-17b, scientists can learn more about how planets change over time, how they interact with their stars, and what conditions might make a planet habitable or uninhabitable. HD 209458b, the pioneering transiting giant. HD 209458b, nicknamed Osiris, is a gas giant orbiting a sun-like star about 159 light-years away in the constellation Pegasus. When it was discovered in 1999, HD 209458b represented a breakthrough in planetary science, becoming the first exoplanet observed through the transit method. This discovery provided scientists with an entirely new way to study planets beyond the solar system, revealing important details about their atmospheres, size, and structure. The planet is about 30% more massive than Jupiter, but significantly larger in size. It completes one full orbit in just 3.5 Earth days. Before Osiris, exoplanets were mainly discovered using the radial velocity method, which detects the slight wobble of a star caused by an orbiting planet's gravitational pull. While this method confirmed the existence of planets, it did not provide much information about their physical characteristics. The transit method, however, allowed scientists to measure a planet's size for the first time. When Osiris passed in front of its star, the light from the star dimmed slightly, revealing the planet's presence. By analyzing how much light was blocked, scientists were able to determine its diameter. As the planet transited, some of the star's light passed through its atmosphere before reaching telescopes on Earth. By analyzing the changes in light, scientists were able to identify the gases present in the planet's atmosphere. This was a groundbreaking moment in exoplanet research because it proved that atmospheric composition could be studied even for planets light-years away. Osiris also provided evidence of high-altitude clouds and winds in its atmosphere. Scientists found that the planet's upper layers are constantly shifting due to powerful winds moving at thousands of kilometers per hour. These winds redistribute heat around the planet, creating extreme temperature differences between the day and night sides. Because the planet is tidally locked, meaning the same side always faces its star, the day side is exposed to continuous sunlight while the night side remains in darkness. The high-speed winds help transport heat from the day side to the night side, preventing the planet from becoming even hotter. Another important discovery related to Osiris was the detection of carbon and oxygen in its atmosphere. The presence of carbon dioxide, carbon monoxide, and water vapor provided insight into how planets form and evolve in extreme environments. It also raised questions about how common certain atmospheric conditions might be in other exoplanets. The ability to analyze atmospheric composition is crucial for future research, especially in the search for habitable planets. Unlike Jupiter, which has well-defined cloud bands, Osiris appears to have a more uniform, hazy atmosphere. Different temperature conditions, chemical compositions, and levels of radiation can create a wide variety of planetary atmospheres, making each exoplanet unique. It was one of the first exoplanets studied by the Hubble Space Telescope, and later observations with the Spitzer Space Telescope and other instruments have provided even more details about its atmosphere and structure. As telescope technology advances, researchers are able to study exoplanets with increasing precision, making Osiris a valuable benchmark for comparing other gas giants. The discoveries made through HD 209458b have influenced how scientists approach exoplanet research. The transit method has since become one of the most effective ways to find exoplanets, leading to the discovery of thousands of new worlds. The ability to analyze planetary atmospheres has also paved the way for future studies of potentially habitable planets, where scientists can look for signs of life by searching for key atmospheric molecules such as oxygen and methane. Betelgeuse, the iconic red supergiant, and its enigmatic fate. Betelgeuse is one of the most famous stars in the night sky. Easily visible to the naked eye as a bright red point in the constellation of Orion, it has fascinated astronomers and skywatchers for millennia. Its distinctive reddish glow is the result of its status as a red supergiant, a star in the later stages of its life, approaching the moment when it will reach a dramatic end. Betelgeuse's eventual fate is a subject of great interest, as it is one of the closest massive stars to Earth that is expected to explode as a supernova. The anticipation of this event has made Betelgeuse one of the most closely monitored stars in the universe. With a radius that is about 700 times that of the Sun, if Betelgeuse were placed in the center of our solar system, its outer layers would extend past the orbit of Mars. Its density is extremely low, making it one of the least compact stars in its category. Its outer layers are so diffuse that they are more like a thin cloud than a solid surface. Unlike more stable stars, its brightness fluctuates over time, sometimes appearing significantly dimmer before returning to its usual luminosity. These variations are caused by complex processes within the star's outer layers. The resulting changes in temperature and density affect the star's brightness as seen from Earth. In late 2019 and early 2020, Betelgeuse experienced a dramatic dimming event that captured worldwide attention. The star's brightness dropped to levels never before recorded, leading to speculation that it might be about to explode as a supernova. However, further observations revealed that the dimming was likely caused by an immense cloud of dust ejected from the star's surface, temporarily blocking its light from our point of view. Despite this false alarm, Betelgeuse is still on a path toward an inevitable explosion. As a red supergiant, it has exhausted the hydrogen fuel that once powered its core. In its final stages, it is fusing heavier elements in a desperate attempt to maintain balance. When it reaches the point where iron forms in its core, fusion will no longer provide the energy needed to counteract the force of gravity. At that moment, the core will collapse in a fraction of a second, triggering a supernova explosion that will send shockwaves through space. This event will be one of the most spectacular astronomical sights ever witnessed by humanity. When Betelgeuse finally explodes, it will shine as brightly as a full moon and may even be visible during the daytime for weeks. The explosion will release an enormous amount of energy, blasting its outer layers into space, while its core collapses into a neutron star or possibly a black hole. Because Betelgeuse is relatively close to Earth in cosmic terms, approximately 640 light-years away, its supernova will be an unprecedented opportunity for astronomers to study the details of such an event in real time. Unlike supernovae in distant galaxies, which are often detected only after they have already peaked in brightness, Betelgeuse's explosion will be observed from the very beginning, providing a wealth of information about the mechanics of stellar death. There is no precise way to predict exactly when this will happen. While estimates suggest that Betelgeuse could explode any time within the next 100,000 years, some models propose that the event could occur much sooner. The challenge lies in the difficulty of pinpointing the internal processes leading up to the final collapse. In addition to its scientific significance, Betelgeuse holds a special place in human culture. As one of the brightest and most recognizable stars, it has been a key feature in mythology and literature for thousands of years. Many ancient civilizations associated it with deities, warriors, or cosmic battles. Its position in the prominent Orion constellation has made it a reference point for navigation and timekeeping throughout history. Its name, derived from Arabic origins, has been popularized in movies, books, and television, further cementing its place in the human imagination. The idea that this massive star will one day explode in a brilliant flash of light adds an element of cosmic drama that few other celestial objects can match. Infrared observations have revealed that Betelgeuse is surrounded by a vast cloud of material it has shed over thousands of years. This material forms a complex structure of dust and gas, creating patterns that tell the story of its past eruptions. As the star continues to evolve, this surrounding nebula will interact with the shockwave from its eventual explosion, producing even more striking features that astronomers will study in the future. Another interesting aspect of Betelgeuse is its movement through space. Unlike many stars that remain relatively fixed in their locations for millions of years, Betelgeuse is moving at high speed through the galaxy. This motion creates a bow shock where the star's expelled material collides with interstellar gas, forming an arc-shaped structure ahead of it. This phenomenon adds another layer of complexity to the study of Betelgeuse's environment. Because of its relatively close distance, there have been questions about whether Betelgeuse's supernova could pose any risk to Earth. However, research has shown that it is far enough away that the explosion will not have any harmful effects on our planet. The radiation and particles released will be absorbed by interstellar space long before they reach our solar system. Instead of being a danger, Betelgeuse's supernova will be an opportunity to witness one of the most powerful events in nature without any adverse consequences. Until that moment arrives, Betelgeuse will continue to be a subject of fascination. With modern telescopes and observation techniques improving every year, astronomers will keep monitoring the star for any signs that it is approaching the final collapse. When the explosion does occur, it will be one of the most widely observed and studied astronomical events in history, offering a once-in-a-lifetime chance to understand the final moments of a massive star. Canis Majoris, the red hypergiant that stuns the cosmos. Canis Majoris is a star of incredible proportions, a red hypergiant that defies expectations and stretches the limits of what a single star can be. Located roughly 3,900 light-years away in the constellation Canis Major, it is one of the largest known stars in the universe. Its sheer size and brightness make it an extraordinary object, standing out even among other supergiants. Unlike regular stars, Canis Majoris is in a rare category known as hypergiants. These stars are much larger and more unstable than the typical supergiants, undergoing extreme changes as they evolve. While the Sun has a diameter of about 1.4 million kilometers, Canis Majoris dwarfs it with an estimated diameter that could reach nearly 1,500 times that of the Sun. If placed at the center of our solar system, it would extend far beyond the orbit of Jupiter and possibly even Saturn. The sheer scale of this star makes it difficult to comprehend, as it challenges the traditional understanding of how massive a star can become before collapsing under its own weight. Its massive size comes with a consequence: a relatively short lifespan. Unlike smaller stars that can burn for billions of years, hypergiants like Canis Majoris consume their fuel at an astonishing rate. It is already in the late stages of its life, meaning it has expanded into a bloated, unstable state and is shedding its outer layers. The star is surrounded by an enormous cloud of gas and dust, a sign of its ongoing mass loss. Over the past few centuries, it has ejected significant amounts of material, forming a complex, ever-changing nebula around it. This is evidence of the violent processes occurring within, as it burns through its remaining fuel and prepares for its eventual fate. As a red hypergiant, it emits a deep red glow, a sign that it is cooler than smaller white or blue stars. However, despite being cooler in temperature, it is still incredibly luminous. It shines with a brightness estimated to be about 200,000 times greater than the Sun. Even though much of its light is scattered or blocked by surrounding dust, it remains one of the most luminous stars of its kind. Many hypergiants do not last long enough to be observed in detail, as they transition quickly from one stage to another before exploding. Canis Majoris is shedding material at a rapid rate, allowing astronomers to study the complex processes that occur before a massive star reaches the end of its life. Eventually, VY Canis Majoris will reach a dramatic conclusion. The most likely outcome is that it will undergo a core collapse, triggering a supernova explosion. When that happens, the energy released will outshine an entire galaxy for a short time, sending shockwaves through space and scattering the elements it has forged throughout its lifetime. Some researchers speculate that instead of a supernova, it could collapse directly into a black hole, skipping the explosion phase altogether. This is a possibility for the most massive stars, as their gravity can be so intense that they do not produce a visible explosion, instead collapsing inward under their own weight. The study of VI Canis Majoris has shown that hypergiants can be highly unstable, with irregular patterns of mass loss and surface activity. Observations suggest that massive convective cells, similar to those seen in smaller stars but on a much larger scale, may be responsible for driving its mass loss. These convective cells cause localized eruptions, where large amounts of material are ejected into space. This phenomenon may explain the formation of the dense nebula surrounding it, as well as the presence of complex molecules detected in its outflow. As the star sheds its outer layers, the ejected material provides a rich environment for chemical reactions. Observations using radio telescopes have detected molecules such as water vapor and carbon-based compounds in the surrounding cloud. This supports the idea that dying stars play a crucial role in enriching the cosmos with elements that eventually contribute to the formation of new stars, planets, and potentially even life. Advances in astronomical imaging and spectroscopy have allowed scientists to observe details that were once impossible to detect. High-resolution images show the asymmetric structure of the material being ejected, indicating that the mass loss is not uniform. This suggests that internal processes, such as stellar rotation and magnetic fields, may be influencing the way the star sheds its outer layers. VI Canis Majoris represents one of the final stages in the life of the most massive stars, a phase that is both violent and beautiful. Every observation brings new insights into how these rare giants behave, helping astronomers refine their understanding of stellar evolution. The study of hypergiants like this one provides a glimpse into the forces that shape galaxies, as the death of such massive stars plays a key role in distributing heavy elements throughout the cosmos. NML Cygni, a shrouded behemoth in the Milky Way. NML Cygni is another red hypergiant that stands among the largest stars ever discovered, a behemoth hidden in the Milky Way's vast cosmic landscape. It resides about 5,300 light-years from Earth in the constellation Cygnus, a region rich in stellar activity where massive stars are born, evolve, and eventually meet their dramatic fates. Though its size and brightness make it extraordinary, NML Cygni remains largely hidden from view. Unlike other famous supergiants, its light is smothered by a dense cloud of gas and dust, making it one of the most enigmatic stars in the sky. Despite being obscured, NML Cygni has drawn great interest from astronomers due to its staggering proportions. This star is a true giant, with an estimated radius that could stretch anywhere from 1,100 to 1,600 times that of the Sun. The sheer immensity of NML Cygni defies easy comprehension, making it one of the best real-world examples of just how massive stars can become before they reach the limits of stability. NML Cygni is losing its outer layers at an astonishing rate. This continuous shedding of material forms a thick shell around the star, which is why it appears so dim in visible light despite its immense luminosity, which is approximately 250,000 times greater than our Sun. The surrounding dust absorbs most of its light and re-emits it in infrared wavelengths, which is the only way astronomers can truly observe its presence. The dense shroud around NML Cygni makes it unique among hypergiants. Most massive stars are relatively easy to study because they radiate enormous amounts of light across the spectrum. But NML Cygni's surrounding dust envelope acts as a cosmic barrier, masking its true nature. This has made determining its exact size, mass, and composition a challenge. Observations using infrared telescopes, such as the Spitzer Space Telescope, have helped researchers pierce through the dust, revealing the complex structure of the material ejected from the star. This shell of gas and dust is not uniform. Observations suggest that it is composed of multiple layers, likely shaped by episodes of mass loss over time. The outer regions contain molecules like water vapor and carbon monoxide, forming a cool, dense environment around the star. Unlike smaller stars, which have relatively stable outer layers, hypergiants are constantly in flux. Their outer atmospheres are often chaotic, with massive plumes of gas rising and falling, driven by internal processes that are still being studied. This instability is part of what makes stars like NML Cygni so fascinating. The sheer scale of its mass loss is remarkable. Estimates suggest that NML Cygni is losing material at a rate thousands of times higher than that of the Sun's solar wind. This means that over time, it has ejected a significant portion of its original mass, forming a nebula-like structure around itself. As this material drifts away, it interacts with surrounding gas clouds, creating intricate patterns that can be observed in infrared and radio wavelengths. Hypergiants like this do not follow the same evolutionary path as smaller stars. Instead of transitioning smoothly into a supernova, they undergo a prolonged period of instability, shedding material in violent bursts before eventually reaching a breaking point. When that moment arrives, NML Cygni will likely end in a spectacular supernova explosion, releasing an enormous amount of energy and scattering its enriched material throughout space. One of the biggest questions surrounding NML Cygni is whether it will produce a traditional supernova or collapse directly into a black hole. If instead of producing a visible explosion, it implodes into a black hole, NML Cygni's death would be nearly invisible, detectable only through gravitational waves or other indirect signals. Regardless of how it meets its end, the legacy of NML Cygni will be imprinted on the cosmos. The elements forged within its core, carbon, oxygen, and heavier elements like silicon and iron, will eventually be released into space, contributing to the formation of new generations of stars and planets. In a way, massive stars like NML Cygni are the cosmic engines of creation, producing the raw materials needed for life to emerge elsewhere in the universe. The Cygnus constellation is home to several high-mass stars, including the famous Cygnus OB2 association, a cluster containing some of the brightest and most powerful stars in the galaxy. This suggests that NML Cygni formed in an environment rich in stellar activity, possibly as part of a larger group of giant stars that evolved together over millions of years. Studying its relationship with nearby stars can provide valuable insights into how massive stars form, interact, and eventually disperse throughout the galaxy. VX Sagittarii, pulsations of a galactic giant. Located roughly 5,000 light-years away in the constellation Sagittarius, VX Sagittarii is anything but stable. Unlike other large stars that maintain a relatively steady size and brightness, VX Sagittarii constantly changes, expanding and contracting. Its radius fluctuates significantly, anywhere from 1,000 to 2,000 times the Sun's radius. These changes are not random, but follow a pattern driven by internal forces within the star. As it expands, its outer layers cool, causing the star to appear redder and dimmer. When it contracts, it heats up, becoming slightly more luminous. This cycle repeats over long periods, though the exact duration and extent of these changes are not entirely understood. Most stars, even massive ones, maintain relatively stable luminosity, but VX Sagittarii can change significantly in a short period. Observations have recorded fluctuations of several magnitudes in brightness, meaning that at times it can appear much fainter than expected for a star of its size. These variations are caused by the way energy moves through the star's vast, unstable layers. Deep inside the star, nuclear fusion generates intense heat, creating outward pressure that pushes against the force of gravity trying to collapse the star inward. In a stable star like the Sun, these forces are balanced, allowing it to maintain a consistent size. However, in VX Sagittarii, this balance is disrupted. The star experiences cycles where outward pressure briefly wins, causing it to expand. But as the expansion reaches a peak, gravity pulls it back in. This ongoing struggle results in the star's rhythmic pulsations. Unlike typical pulsating stars, VX Sagittarii does not have a single predictable cycle. Instead, it exhibits irregularities that make it difficult to model. The variations in its pulsations suggest that multiple processes are occurring simultaneously within the star's interior. As it expands and contracts, VX Sagittarii sheds large amounts of material into space. Observations of VX Sagittarii's surroundings reveal clouds of gas and dust that were once part of the star itself, evidence of the ongoing process of stellar shedding. VX Sagittarii is often surrounded by a thick envelope of dust, which can obscure its true brightness when viewed in visible light. However, in infrared wavelengths, where dust is more transparent, the full extent of its luminosity becomes clearer. At some point, its internal fusion processes will no longer be able to counteract the force of gravity, leading to a catastrophic collapse. The remnants of a supernova explosion could leave behind a neutron star or a black hole, depending on how much mass the star retains before its final collapse. Some of the most famous supernova progenitors, such as Betelgeuse, have shown similar irregular pulsations in the years or decades leading up to their explosions. If VX Sagittarii follows a similar pattern, astronomers may be witnessing one of the final stages before a massive stellar detonation. However, predicting the exact timing of such an event is incredibly difficult. It could happen within our lifetimes, or it may still be thousands of years away. By observing its pulsations, astronomers can refine their models of stellar interiors, learning more about the forces that drive instability in giant stars. Dyson Sphere Dreams, harnessing the energy of VY Canis Majoris, a star of VI Canis. Majoris' scale represents an almost unimaginable source of energy, one that, in theory, could power an entire advanced civilization. If an intelligent civilization were capable of building such a structure around VY Canis Majoris, the possibilities would be almost limitless. The Dyson sphere concept was first proposed by physicist Freeman Dyson in 1960. He speculated that a sufficiently advanced civilization, classified as a Type II civilization on the Kardashev scale, would eventually need to capture all of the energy emitted by its home star to meet its growing power demands. Instead of relying on planetary resources, this civilization might construct an enormous shell or swarm of satellites around the star, absorbing and redirecting its energy for use. In the case of a hypergiant like VY Canis Majoris, the energy potential would be staggering, millions of times greater than what Earth receives from the Sun. Building a Dyson sphere around such a star would require overcoming challenges beyond anything humanity has ever attempted. The sheer scale of the structure is difficult to comprehend. A simple solid shell encasing the entire star is often considered impractical because of the immense gravitational and thermal stresses involved. Instead, scientists and futurists have proposed the idea of a Dyson swarm, a vast collection of satellites, mirrors, and energy-collecting stations that orbit the star in a coordinated manner. This approach would allow for gradual construction and expansion, making it more achievable over time. A Dyson swarm around VY Canis Majoris would need to be positioned at a considerable distance to avoid destruction by the star's intense radiation and solar winds. This hypergiant is nearing the end of its life, shedding massive amounts of material in unpredictable outbursts. Any structure placed too close would be at constant risk of being torn apart by these violent ejections. Engineers designing such a project would need to account for these instabilities, perhaps by positioning the energy-collecting satellites at a safe distance where they could adjust their orbits as needed. The materials required for such a megastructure would be another significant hurdle. A Dyson swarm would likely require planetary-scale resources, perhaps entire asteroids, moons, or even planets dismantled and converted into construction materials. The inner planets of a solar system, along with asteroid belts, would serve as prime candidates for this kind of large-scale resource extraction. Advanced manufacturing techniques, such as nanotechnology or self-replicating robotic assemblers, might be necessary to create the sheer number of structures needed to surround a star of this magnitude. The energy collected from Canis Majoris would need to be transmitted in an efficient manner. One possible method involves beaming the energy as directed laser or microwave radiation toward receiving stations located on planets, space stations, or other structures throughout the civilization's domain. Another approach could involve using energy storage satellites that collect and distribute power as needed. Regardless of the method, the ability to control and distribute such an enormous amount of energy would be a critical part of making the Dyson swarm a functional reality. If a civilization were capable of constructing such a megastructure, its technological capabilities would be beyond anything currently imagined. This would be a society that had moved past dependence on fossil fuels or even nuclear power, instead drawing directly from the most fundamental force in its cosmic neighborhood. The energy harnessed from a star like Canis Majoris could sustain planetary-scale industries, power interstellar travel, or even enable the engineering of entirely new artificial worlds. Such a civilization might be able to manipulate matter on a grand scale, altering planetary environments or even extending the lifespans of stars themselves. Despite the theoretical nature of Dyson spheres, astronomers have searched for signs of such structures around distant stars. One approach is to look for stars that exhibit unusual light patterns, where some of their emitted energy appears to be missing. If an artificial structure were absorbing a significant fraction of a star's light, it might create a signature distinct from natural astrophysical processes. Some researchers have speculated that certain unexplained dimming events observed in space, such as those seen around Tabby's star, could be caused by partial Dyson-like structures. However, no definitive evidence of a Dyson sphere has been found to date. If a Dyson swarm were built around Canis Majoris, its presence would likely be detectable from great distances. A civilization capable of constructing such a massive project might also engage in other large-scale engineering feats, such as reshaping planetary orbits, creating artificial habitable zones, or even altering the composition of their host star to extend its lifespan. Such activities could leave visible traces either through unusual infrared emissions, strange gravitational signatures, or anomalies in the star's brightness. A Dyson sphere or swarm around Canis Majoris would also have a limited lifespan due to the nature of the star itself. Unlike smaller, more stable stars, Canis Majoris is expected to explode as a supernova in the relatively near future, at least on cosmic timescales. When it does, it will release more energy in a matter of seconds than it produced over its entire lifetime. If an advanced civilization had built a Dyson swarm around it, they would need to plan for the eventual destruction of their megastructure or develop ways to harness even the explosion itself. Some theorists have speculated that an ultra-advanced civilization might even attempt to control or delay the supernova process. While humanity is still far from reaching such a level of advancement, the Crab Pulsar, a compact beacon from a stellar catastrophe. The Crab Pulsar is one of the most well-studied neutron stars in the universe. It is the collapsed core of a massive star that ended its life in a brilliant explosion, leaving behind an incredibly dense, fast-spinning remnant. Unlike the massive hypergiants that once burned brightly for millions of years, the Crab Pulsar is a stark contrast, small, yet unimaginably powerful. This pulsar was formed in the aftermath of a supernova recorded by Chinese astronomers in 1054 CE. The explosion was so bright that it was visible in the daytime sky for weeks and at night for nearly 2 years. What remained after the explosion was a rapidly spinning neutron star, only about 25 kilometers across, but with a mass greater than that of the Sun. Despite its size, the Crab Pulsar exerts an immense influence on its surroundings, shaping the nebula of glowing gas that still expands outward from the original supernova. At the heart of the Crab Nebula, this pulsar is a rotating beacon of energy. Like other pulsars, it emits beams of electromagnetic radiation from its magnetic poles. These beams sweep across space like a cosmic lighthouse, appearing as regular flashes of light when they pass Earth. The Crab Pulsar rotates at an astonishing rate of 30 times per second, meaning it completes one full spin in just 33 milliseconds. This rapid rotation is a result of the conservation of angular momentum. When the original star collapsed, its core shrank dramatically, causing it to spin faster in the same way a figure skater speeds up when pulling their arms inward. The pulses from the Crab Pulsar are detected across multiple wavelengths, from radio waves to visible light and even into the X-ray and gamma-ray spectrum. This extreme range of emissions makes it one of the brightest pulsars ever observed. The energy it releases is enough to keep the Crab Nebula glowing, illuminating the surrounding space with a constant stream of radiation. Unlike normal stars, which generate energy through nuclear fusion, a pulsar's power comes from its rapid rotation and strong magnetic field. The Crab Pulsar has an extraordinarily powerful magnetic field, about 1 trillion times stronger than Earth's. This field accelerates charged particles to nearly the speed of light, creating intense electromagnetic radiation. The pulsar's beams of energy are so strong that they influence the entire Crab Nebula, energizing the gas and making it one of the most studied remnants of a stellar explosion. One of the most fascinating aspects of the Crab Pulsar is its occasional glitches. Normally, the pulsar's rotation slows down gradually as it loses energy over time. However, every so often it experiences a sudden increase in rotation speed before gradually settling back into its previous pattern. These glitches are believed to occur due to interactions between the pulsar's crust and its superfluid interior. Scientists study these irregularities to understand the complex physics of neutron stars, which exist under conditions far more extreme than anything we can replicate on Earth. Because its pulses arrive at such a steady rate, astronomers use it as a natural clock to test theories of physics. In particular, pulsars like this one help researchers study the effects of general relativity. The precision of its pulses allows astronomers to measure tiny distortions in spacetime caused by massive objects like black holes. Even though the Crab Pulsar is only about 1,000 years old, a blink of an eye in cosmic terms, it represents a crucial phase in the life cycle of massive stars. While hypergiants like VY Canis Majoris and Betelgeuse will eventually explode in supernovae and leave behind similar remnants, the Crab Pulsar provides a real-time glimpse into what happens after that final, violent event. Neutron stars like the Crab Pulsar are among the densest objects in the universe. A single cubic centimeter of neutron star material, the size of a sugar cube, would weigh about 1 billion tons on Earth. The extreme pressure inside a neutron star crushes protons and electrons together, forming a sea of neutrons packed into an unimaginably small volume. This makes neutron stars unique laboratories for physics, as their interiors are thought to contain states of matter not found anywhere else. The Crab Pulsar is also a source of high-energy cosmic rays. Particles accelerated by the pulsar's intense magnetic field are flung into space at nearly the speed of light. Some of these cosmic rays eventually reach Earth, where they are detected by observatories. Studying these particles helps scientists understand the most energetic processes in the universe, including how matter behaves in extreme environments. Because of its youth and brightness, the Crab Pulsar is one of the most observed neutron stars in the sky. Space telescopes such as Hubble, Chandra, and Fermi have all studied its structure and emissions extensively. The pulsar's powerful bursts of energy have even been used to calibrate instruments on telescopes, serving as a stable reference point for high-energy astrophysics research. While other pulsars exist throughout the universe, Few are as well documented as the Crab pulsar. Its unique combination of rapid rotation, intense magnetic field, and bright emissions makes it a crucial object for studying the nature of collapsed stars. Over time, its rotation will gradually slow as it loses energy, but for now, it remains one of the most powerful beacons in the cosmos. The Crab pulsar stands as a stark contrast to the giant stars that precede it. While stars like NML Cygni and VX Sagittarii dominate the sky with their immense size and brightness, the Crab pulsar represents what comes after their fiery demise. It is a reminder that even in death, a star can leave behind an extraordinary legacy, one that continues to shape the universe long after its initial explosion. TUN 618, spotlight on one of the universe's largest black holes. TUN 618 is a quasar, a bright, energetic beacon powered by a supermassive black hole at its center. Among the many quasars scattered across the cosmos, TUN 618 stands out because of the sheer size of its black hole. Estimated to have a mass of more than 40 billion times that of the Sun, it is one of the largest black holes ever discovered. Quasars like TUN 618 are among the brightest objects in the universe, despite being powered by something that does not emit light on its own. At their core, they are fueled by the immense gravitational pull of supermassive black holes, which consume vast amounts of gas and dust from their surroundings. As this material falls toward the black hole, it forms an accretion disk, a spiraling mass of heated matter that glows due to the intense friction and pressure. The energy released in this process is so powerful that it outshines entire galaxies, making quasars visible from billions of light-years away. TUN 618's light has traveled across the universe for over 10 billion years, meaning that what we see today is an image of the quasar as it was when the universe was still young. It resides in a distant, ancient part of the cosmos, a time when galaxies were forming at a rapid pace and supermassive black holes were growing at extraordinary rates. The fact that TUN 618's black hole was able to reach such an immense size in such a short cosmic time is a mystery that challenges existing theories of black hole formation. Most known supermassive black holes, even the ones at the hearts of giant galaxies, range from a few million to a few billion solar masses. The black hole at the center of the Milky Way, Sagittarius A star, is about 4 million times the mass of the Sun, tiny in comparison to the behemoth in TUN 618. Even the enormous black hole in the giant elliptical galaxy M87, which was the first to be imaged directly, is only about 6.5 billion solar masses. TUN 618's black hole dwarfs them all, raising the question of how such a monstrous object could have formed so quickly. One possibility is that TUN 618's black hole started as a much smaller seed black hole in the early universe and grew rapidly by feeding on vast amounts of matter. Another idea suggests that it may have formed from the collapse of an early supermassive star, a type of object that may have existed in the universe's infancy. If such stars were hundreds of thousands of times more massive than the Sun, their direct collapse into a black hole could have created the foundation for these giants. TUN 618's accretion disk produces an incredible amount of energy, blasting radiation across the electromagnetic spectrum. This radiation ionizes surrounding gas, creating what is known as a quasar's emission lines, bright signatures that allow astronomers to determine its distance, speed, and composition. The brightness of TUN 618 suggests that its black hole is consuming matter at an astonishing rate. Some estimates suggest it is devouring the equivalent of several suns per year, a rate far beyond what is typically observed in other black holes. Its intense energy output creates massive jets of charged particles that travel at nearly the speed of light. These jets can extend for thousands of light-years, shaping the structure of the surrounding space. Quasars like TUN 618 are thought to play a crucial role in galaxy evolution, as their powerful radiation and winds can either fuel or suppress star formation in their host galaxies. Despite its enormous mass, Ton 618 is invisible to the human eye, like all black holes. Its presence is inferred only through the immense energy it releases as it pulls in matter. The event horizon of this black hole, the point beyond which nothing can escape, is thought to be hundreds of billions of kilometers across. Even light, traveling at 300,000 kilometers per second, would take days to cross its immense boundary. If Ton 618's black hole has already reached such an extreme mass, could even larger black holes exist somewhere in the universe? Some scientists speculate that the most massive black holes may have already passed the limits of detection, hidden deep within the centers of the most distant and obscured galaxies. The gravitational forces near its event horizon are so intense that space-time itself is warped in ways that challenge our understanding of the universe. The immense pressure and energy involved in its accretion process create conditions that cannot be replicated in any laboratory on Earth. Studying quasars like Ton 618 helps scientists refine theories about relativity, quantum mechanics, and the fundamental nature of matter. Even though it is billions of light-years away, Ton 618's discovery provides a glimpse into the early universe and the powerful forces that shaped its evolution. Objects like Ton 618 remind us of the extreme nature of cosmic phenomena. It is a testament to the power of black holes, the energy of quasars, and the ongoing mysteries that drive our exploration of the cosmos. Holmberg 15a, the gargantuan black hole anchoring a giant galaxy. Holmberg 15a is a massive elliptical galaxy located in the Abell 85 galaxy cluster, roughly 700 million light-years from Earth. At its heart lies one of the most colossal black holes ever discovered, an object so immense that it rivals some of the largest known black holes in the universe. This black hole is estimated to be at least 40 billion times the mass of the Sun, making it one of the heaviest supermassive black holes ever measured. Unlike the dazzling quasars that shine across billions of light-years, Holmberg 15a's black hole is much quieter. It is not actively consuming large amounts of matter, meaning it does not generate the brilliant light seen in quasars like Ton 618. Instead, it exists in a more dormant state, with occasional infall of material triggering brief bursts of radiation. But its influence extends far beyond its event horizon. The gravitational pull of such a massive black hole affects the stars, gas, and even the dark matter that makes up Holmberg 15a, playing a crucial role in shaping the galaxy's structure. Holmberg 15a itself is an unusual galaxy. It belongs to a class of giant elliptical galaxies known as brightest cluster galaxies, or BCGs. These are the dominant galaxies at the centers of galaxy clusters, formed through the merging of many smaller galaxies over billions of years. As these galaxies collide and combine, their central black holes can also merge, leading to the formation of ultra-massive black holes like the one in Holmberg 15a. The sheer size of Holmberg 15a's black hole raises questions about how it reached such a staggering mass. The leading theory is that it grew through a combination of accretion, drawing in gas and dust over millions of years, and merging with other black holes. When galaxies collide, their central black holes gradually drift toward each other, eventually coalescing into a single, larger black hole. This process may have repeated multiple times in the history of Holmberg 15a, leading to its extraordinary size. The galaxy itself is strikingly diffuse, with a relatively low concentration of stars in its core compared to other elliptical galaxies. This suggests that past mergers may have ejected many stars from the central region, leaving behind a more sparse and extended structure. Some models suggest that when two supermassive black holes merge, they can give a gravitational kick to surrounding stars, flinging them outward and reducing the overall stellar density near the center. This process, known as core scouring, could explain why Holmberg 15a's inner region appears less crowded than expected. Despite its distance, scientists have been able to estimate the size of Holmberg 15a's black hole by studying the motions of stars near its core. The way these stars orbit and move provides clues about the unseen mass influencing them. In the case of Holmberg 15a, the speed and distribution of these stars suggests the presence of an enormous black hole, far beyond the size of those found in ordinary galaxies. Many supermassive black holes in the centers of galaxies are surrounded by dense disks of gas and dust, which feed the black hole and generate enormous amounts of radiation. In Holmberg 15a, there appears to be relatively little gas available for accretion. This could be a result of past mergers that strip the galaxy of its available gas, or it may be that the black hole has already consumed most of the material in its immediate surroundings. The discovery of such an enormous black hole within a relatively quiet galaxy provides a valuable opportunity to study the relationship between black holes and their host galaxies. While much attention is given to quasars and actively feeding black holes, objects like Holmberg 15a show a different side of the equation, one where a black hole has reached a state of equilibrium with its galaxy. The fact that Holmberg 15a harbors a black hole of at least 40 billion solar masses suggests that some black holes may grow much larger than previously thought. If more objects like Holmberg 15a exist, it could mean that the upper limits of black hole mass are far greater than current theories predict. Studying Holmberg 15a and other massive elliptical galaxies can provide insights into the long-term evolution of galaxies and their central black holes. As the universe continues to expand, galaxies like Holmberg 15a will likely remain relatively unchanged for billions of years, acting as cosmic relics that preserve information about the early processes that shaped them. Future telescopes, including those designed to study gravitational waves, may help uncover more details about galaxies like Holmberg 15a. If its black hole did form through multiple mergers, it may have left behind detectable gravitational wave signatures that could provide direct evidence of its violent past. Phoenix A. Unraveling the mysteries of a cosmic black hole. Phoenix A is a supermassive black hole at the center of the Phoenix Cluster, a galaxy cluster located roughly 5.7 billion light-years from Earth. At potentially nearly 100 billion times the Sun's mass, it is one of the most powerful and active black holes ever observed, releasing enormous amounts of energy into its surroundings. Unlike some of the quieter, dormant black holes found in massive elliptical galaxies, Phoenix A is still consuming matter at an astonishing rate. This feeding process makes it one of the brightest sources of X-rays in the known universe. The power of this black hole is not just in its mass, but in the way it interacts with the cluster around it, defying expectations of how supermassive black holes behave over time. In most galaxy clusters, central black holes regulate star formation by heating surrounding gas and preventing it from cooling and collapsing into new stars. This process, known as feedback, ensures that most of the gas in the cluster remains too hot to condense. However, Phoenix A seems to be an exception. Despite its extreme energy output, the Phoenix cluster is undergoing rapid star formation, producing stars at an unusually high rate. This suggests that the black hole is not suppressing star formation as effectively as expected, leading researchers to question whether some black holes operate differently from the standard model. One of the most striking features of Phoenix A is the vast amount of energy it releases through high-speed jets and radiation. These jets, composed of charged particles traveling at nearly the speed of light, extend outward from the black hole, influencing the surrounding gas. In most galaxy clusters, such jets carve out enormous cavities in the hot gas, disrupting the formation of stars. However, in the Phoenix cluster, these jets appear to be less effective at stopping star formation, which raises questions about why the cooling process continues so efficiently. Most supermassive black holes slow down their growth after reaching a certain size, as their feedback mechanisms regulate their environments. Phoenix A, however, appears to be in a phase of rapid growth, consuming large amounts of matter and emitting massive bursts of energy. Perhaps other galaxy clusters have gone through similar phases in the past, with black holes cycling through periods of intense activity before settling into more stable states. The Phoenix cluster itself is an unusual environment, with a much higher star formation rate than other galaxy clusters. This may be due to a combination of factors, including the density of gas in the cluster, the influence of Phoenix A's jets, and the cluster's overall structure. Unlike in clusters where black holes completely suppress star formation, the Phoenix cluster presents a more complex balance between heating and cooling. One of the biggest mysteries surrounding Phoenix A is how it has managed to sustain such high levels of activity for so long. Most supermassive black holes eventually enter a state where they regulate their growth by preventing excessive amounts of gas from falling in. However, Phoenix A continues to accrete matter at an incredible pace, suggesting that its environment provides a steady supply of fuel. The source of this fuel remains a subject of study, with scientists investigating whether the cluster's structure allows gas to flow toward the black hole more efficiently than in other systems. The discovery of Phoenix A has also led to new discussions about the upper limits of black hole mass. With it potentially being the most massive black hole ever found, its rapid growth suggests that some black holes may continue accumulating matter far beyond what was previously thought possible. Do even larger black holes exist in the universe, hidden in the centers of distant galaxy clusters that have not yet been fully explored? If it continues to consume matter at its current rate, it could eventually deplete the available gas in the Phoenix cluster, shutting down star formation entirely. This would transform the cluster into a much more inactive system, similar to other older galaxy clusters where little new star formation occurs. However, if Phoenix A operates differently from other black holes, it may continue driving star formation for much longer than expected. Telescopes capable of detecting high-energy radiation, such as the Chandra X-ray Observatory, have provided detailed images of the black hole's jets and the surrounding gas. Upcoming missions, including next-generation space telescopes, may help unravel some of the deeper mysteries of how Phoenix A interacts with its environment. By studying this black hole, scientists will gain a better understanding of the role supermassive black holes play in shaping the cosmos. While many black holes follow predictable patterns of growth and regulation, Phoenix A shows that there are exceptions, objects that challenge our understanding of how these massive entities evolve. As researchers continue to study this extraordinary black hole, they may uncover new insights that reshape our theories about the formation and behavior of the most powerful objects in the universe. IC 1101, the colossal galaxy that redefines scale. IC 1101 is one of the largest known galaxies in the universe, a true titan among galactic structures. Located about 1 billion light-years away in the center of the Able 2029 galaxy cluster, it dwarfs most other galaxies, stretching an estimated 500,000 light-years across. For comparison, the Milky Way is about 100,000 light-years wide, meaning IC 1101 could contain our galaxy about 5 times over. Unlike spiral galaxies with distinct arms, IC 1101 is classified as a giant elliptical galaxy. Elliptical galaxies tend to form through the merging of smaller galaxies, and IC 1101 is a prime example of this process. Over billions of years, it has absorbed countless neighboring galaxies, growing in size and mass with each collision. These mergers have stripped it of the beautiful spiral arms seen in galaxies like the Milky Way, leaving behind a vast, smooth, and nearly featureless structure. What remains is a massive cloud of ancient stars, stretching far beyond the typical boundaries of most galaxies. The galaxy appears a dull yellowish hue, indicating that its stars are mostly old and that new star formation has largely ceased. This is a common trait of giant elliptical galaxies, as the violent interactions that built them also tend to use up or expel much of their gas. Without an ample supply of fresh gas to form new stars, IC 1101 is a galaxy in its later stages of life, populated mostly by older, cooler stars that burn dimly compared to the bright blue stars found in younger galaxies. At the heart of IC 1101 lies a supermassive black hole, likely one of the most massive in the known universe. While its exact size is difficult to determine, it is almost certainly billions of times the mass of the Sun. This central black hole plays a key role in shaping the galaxy, as its immense gravitational pull can influence the motion of surrounding stars and regulate any remaining gas. If IC 1101 had more available gas, the black hole might generate powerful jets, similar to those seen in active galactic nuclei. However, the lack of significant star formation suggests that much of the available gas has either been consumed or ejected into intergalactic space. The Milky Way is estimated to contain about 1 trillion stars, but IC 1101 could contain as many as 100 trillion. This staggering number gives it an immense gravitational influence, holding together a vast collection of stars, planetary systems, and remnants of past collisions. The galaxy's outer regions fade gradually into intergalactic space, making it difficult to determine its precise boundary. Some stars that appear to belong to the galaxy may in fact be part of a vast intergalactic population, drifting without a clear home. Like all large galaxies, it contains far more mass than can be accounted for by its stars and visible matter alone. This suggests that dark matter, an unseen form of mass that does not emit or interact with light, plays a crucial role in holding the galaxy together. Without dark matter, the outer stars of the galaxy would not be able to orbit at the speeds they do without escaping into space. The vast size of IC 1101 means that it likely contains an immense halo of dark matter, extending far beyond the visible stars. IC 1101 is not just large, it is also incredibly luminous, emitting a vast amount of light from its countless stars. However, its overall brightness is spread out over such a large volume that it does not appear overwhelmingly bright in telescopes. Instead, it has a diffuse glow, stretching across the sky in long exposure images. This makes it challenging to study in detail, as its outer edges blend into the background of space. Despite this, observations have revealed the remnants of past interactions, such as faint shells and streams of stars that hint at the smaller galaxies it has absorbed over time. Galaxy mergers are still occurring in the universe, and as long as it remains at the center of a galaxy cluster, IC 1101 may continue to grow. However, as the universe expands, galaxies are moving farther apart, reducing the likelihood of future mergers. At some point, IC 1101 may reach a limit where it no longer significantly increases in size. It could become one of the last great galactic giants, a relic of an earlier era when galaxies frequently collided and merged. IC 1101 provides a glimpse into the possible future of many large galaxies, including our own. The Milky Way is on course to collide with the Andromeda Galaxy in about 4.5 billion years, and this event will reshape both galaxies, likely forming a single massive elliptical galaxy. While this future galaxy will not reach the size of IC 1101, it will share many of the same characteristics: an older population of stars, a powerful central black hole, and a gradual fading of its outer edges into intergalactic space. ESO 146-5, an enormous elliptical in the local cosmos. ESO 146-5 is a massive elliptical galaxy that resides in our cosmic neighborhood. Though it may not be as famous as some of the largest galaxies in the universe, it is still a giant in its own right, dominating the region it inhabits. Instead, its claim to fame is its sheer mass. At around 27 trillion solar masses, it is one of the most massive galaxies in the universe. Instead of elegant sweeping arms filled with new stars, elliptical galaxies appear as vast, rounded clouds of older stars, with little evidence of the active star formation that characterizes galaxies like the Milky Way. The formation of ESO 146-5, like other large elliptical galaxies, is thought to be the result of countless mergers over billions of years. This process has given ESO 146-5 an immense rounded appearance, stretching far across the void and making it one of the most prominent objects in its local region. ESO 146-5 has a yellowish or reddish hue, which is a direct result of its age. The stars within it have been burning for billions of years, and many of the hottest, most short-lived stars have already exhausted their fuel. What remains are older, cooler stars, giving the galaxy its characteristic appearance. Without a fresh supply of material, new stars do not form at the same rate as they do in spiral galaxies, leading to a population dominated by ancient stars. The visible portion of the galaxy is just a small part of its total structure. Surrounding it is an extended region of diffuse stars, many of which may have been pulled from other galaxies during past interactions. These faint outer regions make it difficult to determine the exact size of the galaxy, as its boundaries gradually fade into the surrounding space. Even beyond the stars, a vast halo of dark matter is believed to encompass the galaxy, influencing its gravitational field and the movement of other objects nearby. Galaxies like ESO 146-5 are often found at the centers of galaxy clusters, acting as the dominant gravitational force in their local environments. They serve as anchors around which smaller galaxies orbit, drawn in by their immense mass. Over time, some of these smaller galaxies may be pulled too close, merging with ESO 146-5 and contributing to its continued growth. This slow but steady process of galactic cannibalism is a key feature of elliptical galaxies, allowing them to reach enormous sizes over cosmic timescales. Despite its age and lack of new star formation, ESO 146-5 is far from a static object. The stars within it are constantly moving, their orbits influenced by the combined gravitational pull of the galaxy's mass. Some stars follow more random elliptical paths, while others move in more organized motions depending on how the galaxy evolved. Unlike spiral galaxies, where stars largely orbit in a flat plane, the motion within an elliptical galaxy is more chaotic, a reflection of its turbulent history. The Milky Way is currently an active spiral galaxy, but its long-term fate may be similar to ESO 146-5. In a few billion years, it is expected to collide with Andromeda. Over time, additional mergers may further erase any remaining traces of the original spiral structure, leaving behind something more like ESO 146-5, a massive, rounded galaxy filled with aging stars. While much attention is given to galaxies in the most distant reaches of space, where we see them as they existed billions of years ago, nearby examples like ESO 146-5 allow astronomers to study elliptical galaxies in greater detail. By comparing them to their younger counterparts, scientists can piece together the history of galaxy formation and better understand the processes that drive the transformation from spirals to ellipticals. Large elliptical galaxies are often surrounded by extended halos of hot gas detectable in X-ray observations. This gas is thought to be a remnant of past galactic mergers and interactions, gradually heating up as it settles into the gravitational well of the galaxy. In some cases, these halos can provide clues about the environment in which the galaxy formed, revealing details about its past encounters with other galaxies and the larger cosmic structures to which it belongs. Despite its seemingly calm appearance, ESO 146-5 has likely experienced a history of violent events. The remnants of past mergers may still be visible in the form of faint tidal streams, trails of stars stretched out by gravitational interactions. These features are difficult to detect, but with modern telescopes and advanced imaging techniques, astronomers continue to uncover evidence of the dramatic events that have shaped this galaxy over billions of years. The presence of globular clusters around ESO 146-5 is another important clue to its past. These dense collections of stars orbit the galaxy much like satellites, forming a kind of stellar halo around its central mass. The number and distribution of globular clusters can provide insight into how the galaxy grew, as they often preserve information about the earliest periods of galactic evolution. Some of these clusters may even have originated in smaller galaxies that were later absorbed by ESO 146-5, serving as relics of a bygone era. Messier 87, a giant galaxy and its supermassive heart. Located in the Virgo cluster, Messier 87 is among the largest in the local universe, stretching over 120,000 light-years across and containing trillions of stars. It is an active powerhouse housing a supermassive black hole at its heart. This black hole, known as M87 star, is one of the most studied in the cosmos and has a mass of around 6.5 billion times that of the Sun. M87 star consumes matter from its surroundings, drawing in gas, dust, and even entire stars that venture too close. Friction within its accretion disk causes temperatures to rise to extreme levels, emitting powerful X-rays and radio waves detectable from Earth. One of the most striking features of Messier 87 is the massive jet of high-energy particles streaming out from its central black hole. This jet extends for thousands of light-years into space, moving at nearly the speed of light. The source of this jet lies in the intense magnetic fields around M87 star. As material falls toward the black hole, some of it is redirected along these fields and ejected at incredible speeds. This process remains an area of active research, as scientists seek to understand the precise mechanisms that launch these relativistic jets. This jet is visible even through smaller telescopes, appearing as a bright streak extending outward from the core of Messier 87. Observations of this jet have provided key insights into black hole physics, revealing details about the interaction between a black hole and its environment. Unlike a star, which emits light from its own nuclear fusion, the glow of M87's jet comes from charged particles accelerating along magnetic field lines. The black hole at the heart of Messier 87 became famous in 2019 when it became the first black hole ever directly imaged. The Event Horizon Telescope, a network of radio observatories across the globe, captured the first ever visual confirmation of a black hole's event horizon. The image revealed a glowing ring of gas surrounding a dark central region, the shadow of the black hole itself. This historic achievement confirmed long-standing predictions made by Einstein's general theory of relativity and offered humanity its first real glimpse at one of nature's most extreme objects. Stars in the galaxy's central region move at astonishing speeds, caught in the gravitational grip of the supermassive black hole. This rapid motion provides astronomers with a way to estimate the black hole's mass. By tracking the movement of stars and gas around the core, researchers have been able to refine their calculations, confirming M87 star's immense scale. Messier 87 contains more stars than the Milky Way, and its outer regions extend far into intergalactic space. The galaxy's shape is largely the result of its history of mergers. Over billions of years, Messier 87 has absorbed smaller galaxies, incorporating their stars into its vast halo. Its position in the Virgo cluster also makes it a dominant force in its region of space. The Virgo cluster is a massive collection of galaxies, with Messier 87 as one of its central members. Gravity binds the cluster together, and Messier 87's immense mass helps to shape the motion of other galaxies within the cluster. The extended halo of Messier 87 contains numerous globular clusters. These clusters are among the oldest structures in the universe, some dating back more than 10 billion years. By studying them, astronomers gain valuable insights into the history of Messier 87, tracing its evolution through time. The environment around Messier 87 is filled with hot X-ray emitting gas. This gas is a signature feature of galaxy clusters, where gravitational forces have heated the intergalactic medium to extreme temperatures. This plasma glows in X-ray wavelengths, revealing the large-scale structure of the Virgo cluster. The presence of this hot gas suggests that Messier 87 continues to interact with other galaxies in the cluster, stripping gas from smaller neighbors and incorporating it into its own extended halo. The Great Attractor, a mysterious gravitational behemoth. The universe is not a static place. Galaxies are in motion, drawn by gravitational forces that shape their paths over millions and billions of years. One of the most puzzling discoveries in modern cosmology is that the Milky Way, along with countless other galaxies, is moving towards something unseen, something massive, powerful, and hidden from direct observation. This mysterious force is known as the Great Attractor. The Great Attractor is not a single object like a black hole or a massive galaxy. Instead, it is a vast region of space exerting a gravitational pull strong enough to influence entire galaxy clusters. It is located roughly 150 to 250 million light-years away from Earth in the direction of the Centaurus and Norma clusters. Astronomers estimate that the Great Attractor contains a mass equivalent to tens of thousands of galaxies, making it one of the most significant gravitational anomalies in the observable universe. The discovery of the Great Attractor came about in the 1970s and 1980s when astronomers began mapping the motion of galaxies in the local universe. They found that the Milky Way, along with the entire local group of galaxies and even the larger Virgo supercluster, was moving at incredible speeds toward a particular region of space. This movement could not be explained by the gravitational influence of any nearby galaxy or galaxy cluster. Instead, something enormous and hidden appeared to be drawing these structures inward. One of the biggest challenges in studying the Great Attractor is that it lies in a part of the sky obscured by the Milky Way itself. This region, called the Zone of Avoidance, is filled with stars, gas, and cosmic dust, making it difficult to see what lies beyond. Traditional optical telescopes cannot penetrate this thick cosmic barrier, forcing astronomers to rely on other wavelengths of light, such as radio waves and X-rays, to gather information. Early estimates suggested it was a massive supercluster of galaxies, but further observations complicated the picture. The mass distribution in this region is not uniform, and while there are many galaxies present, they do not seem to account for the full gravitational pull being exerted. This has led to alternative theories, including the possibility that unseen dark matter plays a significant role in the region's gravitational influence. If the Great Attractor region contains a high concentration of dark matter, this could explain why it exerts such a strong pull on surrounding galaxies without being directly visible. As astronomers mapped even larger structures in the universe, they discovered that the Great Attractor is part of an even greater gravitational system known as the Laniakea supercluster. Laniakea, meaning immense heaven in Hawaiian, is a vast collection of galaxies, including the Milky Way, stretching over 500 million light-years. Within this supercluster, the Great Attractor appears to be a central gravitational focal point, drawing galaxies toward it. The motion of galaxies toward the Great Attractor is not a straightforward path. It is influenced by the presence of other massive structures, such as the Shapley supercluster, an even larger grouping of galaxies located beyond the Great Attractor. Some studies suggest that while the Great Attractor is pulling galaxies towards it, the overall motion of cosmic structures in this region is also directed toward Shapley, which may be an even more dominant force. The study of the Great Attractor is crucial for understanding the large-scale structure of the universe. Galaxies are organized into an intricate cosmic web, with vast voids separating immense clusters and superclusters. The Great Attractor represents one of the strongest concentrations of mass in this web, demonstrating how gravity shapes the universe on enormous scales. The Earth orbits the Sun at about 30 kilometers per second, and the Sun orbits the center of the Milky Way at roughly 220 kilometers per second. But when accounting for the motion of our galaxy within the larger cosmic structure, astronomers have found that the Milky Way is moving toward the Great Attractor at a staggering speed of around 600 kilometers per second. This means that everything in our region of space, the stars, planets, and galaxies we see, are being drawn toward an unseen gravitational force on an unimaginable scale. Despite this movement, the Great Attractor does not pose any immediate threat to our galaxy. The motion of galaxies occurs over timescales of billions of years, and other cosmic forces, including the expansion of the universe, also play a role in shaping their paths. The accelerating expansion of the universe, driven by dark energy, counteracts the pull of massive structures like the Great Attractor, preventing galaxies from simply collapsing into them. Improved infrared and radio telescopes will provide deeper insights into what lies hidden behind the zone of avoidance. By mapping the motion of galaxies with greater precision, astronomers hope to refine their understanding of this immense gravitational force and its role in shaping the universe. The Antennae Galaxies, a spectacular collision of cosmic titans. While stars and planets may seem like permanent fixtures in the night sky, the cosmos is a place of motion, transformation, and sometimes immense collisions. One of the most dramatic examples of this is unfolding 45 million light-years away in the constellation Corvus, where two galaxies, NGC 4038 and NGC 4039, are locked in a spectacular merger. Together, they form what is known as the Antennae Galaxies, a stunning display of cosmic forces in action. The Antennae Galaxies are in the middle of a slow, violent collision. This is not a sudden crash like two cars colliding, but a drawn-out gravitational battle lasting hundreds of millions of years. As these galaxies pass through one another, their stars, gas, and dust are pulled and stretched into long, curving tidal tails that resemble insect antennae, hence their name. These massive tendrils of material are some of the clearest signs of galactic interactions, revealing the incredible power of gravity to reshape entire galaxies. Galactic collisions are not rare in the universe, but the Antennae Galaxies stand out because they represent a particularly chaotic and active stage of such an event. The cores of both galaxies are still visible, but they are no longer separate, distinct structures. Instead, they are being pulled together by mutual gravitational attraction, eventually forming a single, larger galaxy. This transformation is accompanied by a dramatic burst of star formation. As gas clouds collide and compress, they trigger the birth of countless new stars, lighting up the surrounding regions like cosmic fireworks. Observations of the Antennae Galaxies show thousands of bright, young star clusters, some of which are likely to evolve into globular clusters that will survive long after the merger is complete. Many of these newly formed stars are massive and will burn through their fuel quickly, ending their lives in supernova explosions that enrich the surrounding space with heavy elements. This means that the Antennae Galaxies are not just merging, they are actively reshaping the chemical makeup of the next generation of stars and planetary systems. When two galaxies interact, their individual stars do not typically collide because of the vast distances between them. Instead, the gravitational forces from each galaxy pull on the other's structure, distorting their shapes and triggering waves of star formation. The real action happens in the interstellar medium, the clouds of gas and dust that exist between stars. As these clouds slam into each other, they form the building blocks of new stars. By observing them in different wavelengths of light, astronomers can track how energy moves through the merging system. Infrared images reveal hidden star-forming regions obscured by dust, while X-ray observations detect the presence of superheated gas and remnants of exploded stars. Radio telescopes, on the other hand, show the distribution of cold gas, mapping out where future star formation might take place. In many ways, studying the Antennae Galaxies is like looking into the Milky Way's own future. The Milky Way and Andromeda are expected to undergo a series of close encounters before eventually merging into a single, elliptical galaxy. While this may sound dramatic, the process will unfold over such vast timescales that it will not pose an immediate threat to any individual star system, including our own solar system. Many of the largest elliptical galaxies in the universe are thought to have formed from past mergers of smaller galaxies. By studying systems like the Antennae, astronomers can piece together the steps that lead from a spiral galaxy like the Milky Way to the massive, featureless ellipses seen in many parts of the cosmos. Most large galaxies, including both the Milky Way and Andromeda, harbor supermassive black holes at their centers. As galaxies merge, their central black holes are pulled together as well, eventually forming a binary system that spirals inward due to gravitational interactions. In some cases, this process leads to a dramatic collision, releasing an enormous amount of energy in the form of gravitational waves. While the Antennae Galaxies do not yet show clear signs of this happening, their chaotic environment suggests that such an event could occur in the far future. When galaxies merge, their stars are not destroyed, but their orbits can be altered by shifting gravitational forces. Some stars may be flung into intergalactic space, becoming rogue stars that drift through the cosmos alone. Others may be pulled closer to the merging cores, where they experience turbulent environments filled with radiation and intense gravitational forces. While Earth-like planets in such systems might survive, their climates and stability could be drastically affected by these changes. The Antennae Galaxies are close enough to be observed in great detail, yet distant enough that their evolution unfolds over millions of years, providing a window into both the present and the distant past. Every observation adds to our understanding of how galaxies interact, evolve, and ultimately transform into new cosmic structures. Despite the violence of this process, galactic mergers are a fundamental part of the universe's life cycle. They drive the growth of galaxies, enrich the cosmos with newly formed elements, and help shape the structure of the universe on the largest scales. Without these collisions, the galaxies we see today, including our own, would not exist in their current forms. The Coma Cluster, unveiling one of the universe's largest structures. The Coma Cluster is a massive congregation of galaxies located around 320 million light-years away in the constellation Coma Berenices. Containing over 1,000 large galaxies and many thousands of smaller ones, it is one of the most well-studied galaxy clusters in the universe. Unlike a single galaxy, a galaxy cluster is an enormous, interconnected system held together by gravity. The galaxies within the Coma Cluster are not static. They move, interact, and influence one another. Some are spirals, much like the Milky Way, while others are elliptical, featureless, and aged. There are also irregular galaxies with chaotic shapes distorted by past interactions. Many of the galaxies within the cluster show evidence of being shaped by their environment. Some have lost their outer layers of gas, stripped away by the hot plasma that fills the space between galaxies. The Coma Cluster is dominated by two giant elliptical galaxies, NGC 4889 and NGC 4874. These massive galaxies sit near the cluster's center, acting like gravitational anchors around which the rest of the cluster orbits. They are home to large supermassive black holes, each billions of times the mass of the Sun. These central giants likely grew so massive through repeated mergers with other galaxies over billions of years. One of the most striking features of the Coma Cluster is the hot gas that fills the space between its galaxies. This gas is so energetic that it emits X-rays, making the cluster glow brightly in X-ray observations. The presence of this hot gas is a key indicator of the gravitational power of the cluster. Without an immense force holding it in place, this gas would simply disperse into space. The fact that it remains trapped within the cluster tells astronomers something important. There is far more mass in the Coma Cluster than what is visible. Dark matter's presence in the Coma Cluster was one of the first strong pieces of evidence that the universe contains much more mass than what we can directly observe. In smaller, isolated galaxies, star formation can continue uninterrupted for billions of years, as gas is slowly drawn in and turned into new stars. But in a dense environment like the Coma Cluster, the situation is very different. The space between galaxies is filled with hot plasma that can strip away a galaxy's supply of gas as it moves through the cluster. Without this gas, the galaxy loses its ability to form new stars. Many of the galaxies in the Coma Cluster have undergone this process, explaining why the cluster contains so many older red elliptical galaxies rather than younger blue spiral ones. The Coma Cluster is not an isolated system. It is part of an even larger structure called the Coma supercluster, which itself is connected to a vast network of galaxies spanning hundreds of millions of light-years. The universe is built like a web, with galaxy clusters acting as the densest nodes in this vast structure. Between these clusters, immense voids exist, regions where galaxies are scarce, and space stretches almost empty for millions of light-years. The Milky Way is currently part of a much smaller galaxy group called the Local Group, which contains Andromeda, the Triangulum Galaxy, and several dozen smaller galaxies. But over billions of years, the Local Group is expected to merge with other nearby groups and clusters, potentially joining an even larger supercluster. This process mirrors the history of the Coma Cluster, which formed through the gradual accumulation of galaxies over time. Observations from space-based telescopes like Chandra and XMM Newton have mapped the cluster's X-ray emissions, showing the distribution of hot gas and dark matter. Radio telescopes have detected enormous jets of particles streaming from supermassive black holes, further shaping the cluster's internal environment. The Coma Cluster stands as one of the most significant structures in the universe, a vast collection of galaxies bound together by gravity and dark matter. It is a place where galaxies are shaped, transformed, and sometimes even destroyed in the relentless pull of cosmic evolution. It offers a glimpse into the past, a key to understanding the present, and a possible preview of our own galaxy's distant future. Boötes Void, the immense abyss in the cosmic web. The universe is arranged in a vast web-like structure, with galaxies forming along cosmic filaments, interwoven across the universe like threads in an enormous net. In between these filaments there are immense gaps, regions of space that appear almost completely empty. One of the most famous and striking examples of this emptiness is the Boötes Void, a truly vast region of space where galaxies are astonishingly scarce. Located about 700 million light-years from Earth, the Boötes Void is one of the largest voids known in the observable universe. It spans approximately 330 million light-years across, making it one of the greatest cosmic empty spaces ever identified. To put this into perspective, if the Milky Way were placed at the center of the void, it would take over 100 million years for light to reach the nearest known galaxy. That level of emptiness is difficult to grasp, especially when compared to the dense galactic environments of clusters like the Coma Cluster or Virgo Cluster, where thousands of galaxies are packed together in much smaller volumes. In most regions of the universe, galaxies are distributed relatively evenly along filaments, but within the Boötes Void, there are only a handful. When it was first discovered in 1981, astronomers were puzzled. A region this large should contain tens of thousands of galaxies, but extensive searches found only a few dozen scattered across the vast expanse. This raised questions about how such an empty space could have formed. The current understanding is that the Boötes Void, like other cosmic voids, formed as a natural part of the large-scale structure of the universe. In the early universe, matter was not perfectly uniform. It had small variations in density, which allowed gravity to slowly pull material together in some places while leaving others increasingly empty. Over billions of years, gravity strengthened these differences. Dense regions collapsed to form galaxies, clusters, and superclusters, while less dense regions became even emptier, as gravity continued to pull any remaining matter toward the denser parts of space. The Boötes Void likely formed through this process, growing larger over cosmic time as galaxies within it migrated outward toward denser filaments. Despite being called a void, the Boötes Void is not completely empty. There are a few galaxies inside, but they are incredibly isolated. Some of these galaxies are arranged in a small string-like structure within the void, hinting that even in the emptiest parts of the universe, some matter still clings to the cosmic web. However, the environment is vastly different from the typical galactic neighborhood seen elsewhere. In galaxy clusters, interactions between galaxies are common. Collisions, mergers, and gravitational influences shape their evolution. But inside the Boötes Void, galaxies are alone, evolving in near total isolation, untouched by the usual cosmic forces at play in denser regions. Without interactions with other galaxies, how do they evolve? Do they form stars differently compared to galaxies and clusters? Some theories suggest that void galaxies may have retained more of their original gas, since they do not experience the stripping effects seen in more crowded environments. Others speculate that these galaxies may be slower to develop or follow unusual growth patterns due to their isolation. Studying these rare galaxies could provide insight into how galactic evolution differs depending on the surrounding cosmic environment. While it is one of the largest known voids, it is not unique. Similar voids have been discovered, each highlighting the uneven distribution of matter on cosmic scales. The universe is not a smooth sea of galaxies. It is more like a vast foamy network, with dense walls of galaxies enclosing these enormous empty regions. Voids like Boötes help define the shape of the universe. Since voids lack large amounts of normal matter, they are useful places to study how these unseen forces shape the universe. Dark matter is thought to be less concentrated in voids, while dark energy may play an even greater role in these empty regions. By examining the properties of voids, scientists hope to learn more about these unknown components of the cosmos. The Sloan Great Wall, mapping the universe's largest structures. The Sloan Great Wall is a colossal filament of galaxies that spans an astonishing 1.38 billion light-years in length. This immense structure, first identified in 2003 during the Sloan Digital Sky Survey, is one of the most striking examples of how gravity has sculpted the universe on incomprehensible scales. The Sloan Great Wall is not a physical barrier or a single object. It is a massive chain of galaxy clusters and superclusters connected by thin threads of galaxies and dark matter. It is so large that light, traveling at 300,000 kilometers per second, would take over 1 billion years to cross from one end to the other. To grasp the scale of this structure, it helps to compare it to the Milky Way, which is about 100,000 light-years across. The Sloan Great Wall is more than 13,000 times wider. The Sloan Great Wall is made up of multiple galaxy superclusters, vast collections of galaxy groups bound together by gravity. These superclusters themselves are connected by even thinner strands of galaxies, forming a continuous structure that stretches across a significant portion of the observable universe. The galaxies within the wall are not evenly distributed. They clump together in certain areas, creating dense nodes surrounded by relatively empty spaces. One of the most fascinating aspects of the Sloan Great Wall is that it challenges the idea of the cosmological principle, the assumption that the universe is homogeneous and looks roughly the same on large scales. According to this principle, when looking at the universe from a far enough distance, galaxies should be evenly spread out, with no major variations in density. But structures like the Sloan Great Wall suggest otherwise. They reveal that matter in the universe is organized into intricate, interconnected patterns, with enormous differences in density depending on where you look. Current models of cosmic evolution suggest that structures should only be able to grow to a certain size within 13.8 billion years, the age of the universe. Yet the Sloan Great Wall pushes up against that theoretical limit, suggesting that either gravity is even more effective at building large structures than previously thought, or that our understanding of cosmic evolution may still have gaps. The galaxies within the Sloan Great Wall are not just passively sitting in place, they are moving, orbiting, and interacting with each other. Galaxy clusters within the wall are gradually pulling on one another, and over billions of years, some of these clusters may merge, growing even larger. At the same time, the expansion of the universe is stretching the space between galaxies, slowly pulling the structure apart. This interplay between gravity and cosmic expansion shapes the long-term fate of the wall, determining whether it will continue to grow or eventually disperse into smaller, disconnected pieces. By mapping the positions and velocities of galaxies within the wall, astronomers can trace the underlying distribution of dark matter, the invisible substance that makes up most of the universe's mass. Understanding how dark matter is distributed within the wall helps refine models of how the universe evolved from a nearly uniform state into the complex, interconnected structure we see today. The Sloan Great Wall was discovered as part of the Sloan Digital Sky Survey, which mapped only a fraction of the observable universe. There may be even larger structures hidden beyond our current observational limits, waiting to be discovered as telescope technology improves. Each new discovery adds another piece to the puzzle, revealing more about the immense scale and complexity of the cosmos. While much of astronomy focuses on stars, planets, and black holes, large-scale structures reveal the grand architecture of the cosmos, the vast interconnected networks of matter that define the universe on its largest scales. Every filament, cluster, and void tells part of the story of how gravity and time sculpted the universe from a chaotic sea of particles into the intricate cosmic landscape we observe today. Charting the observable universe. Boundaries of cosmic vision. The observable universe is a vast but finite region of space, determined by the limits of what light has had time to reach us since the beginning of the cosmos. Unlike an ordinary physical boundary, this edge is not a solid wall or a distinct cutoff point. It is a horizon shaped by the age of the universe and the speed of light. When astronomers chart the observable universe, they are not just creating a map of what exists, they're also defining the limits of human knowledge, drawing a line between what we can see and what lies forever beyond our reach. The concept of the observable universe is based on the fact that light takes time to travel. When we look at distant galaxies, we are not seeing them as they are today, but as they were millions or even billions of years ago. The farther we look, the deeper we peer into the past. The most distant objects we can observe today are those whose light has traveled for about 13.8 billion years, the age of the universe. However, due to the expansion of space, the actual distance to these objects is far greater. In fact, the cosmic horizon, or the edge of the observable universe, is estimated to be around 46 billion light-years away in every direction. This means that from our vantage point, the entire observable universe spans about 93 billion light-years across. Mapping this immense region is no simple task. Unlike terrestrial maps, which can be drawn with fixed locations and distances, the structure of the cosmos is constantly evolving. Galaxies are moving, space itself is stretching, and light from the early universe is redshifted as it travels through expanding space. To create an accurate representation of the universe, astronomers must account for all these factors, translating their observations into a framework that reflects both distance and time. The process of charting the observable universe begins with nearby objects, stars, planets, and galaxies that can be directly measured with telescopes. For relatively close galaxies, astronomers use a technique called parallax, where slight shifts in an object's position, as seen from Earth at different times of the year, help determine its distance. As we look farther out, other methods come into play. One of the most important is the redshift of light. Because the universe is expanding, light from distant galaxies is stretched, shifting toward the red end of the spectrum. The greater the redshift, the farther away the galaxy is. By comparing redshifts with other distance measurements, astronomers can build a large-scale map of the universe. This cosmic map is not uniform. It reveals a complex web of galaxy clusters, filaments, and vast empty voids. The largest structures, like the Sloan Great Wall, span billions of light-years, while enormous gaps, such as the Boötes Void, seem to contain almost nothing at all. These patterns tell a story of how the universe evolved from an early, nearly uniform state into the vast cosmic web we see today. Beyond galaxies, astronomers also look at the relic radiation from the early universe, known as the cosmic microwave background, or CMB. This faint glow, first detected in the 1960s, is the afterglow of the Big Bang, stretched and cooled over billions of years. By mapping tiny fluctuations in the CMB, scientists can trace the distribution of matter in the early universe, providing a blueprint for how galaxies and clusters later formed. The CMB acts as a boundary of sorts. Beyond it, the universe was still too hot and dense for light to travel freely. This means that, while we can infer what came before, we can never directly observe the universe's earliest moments. One of the most striking aspects of the observable universe is that it is not the entire universe. What lies beyond remains unknown. Because space is expanding, regions that were once visible may now be receding faster than light can reach us. These distant areas, though they may be filled with countless galaxies, are effectively lost to us forever. Even more intriguing is the possibility that the universe is infinitely large, extending far beyond what we can ever detect. If this is the case, our observable universe is just a tiny fraction of a much grander reality. Despite these limitations, astronomers continue to push the boundaries of what can be seen and understood. New surveys, such as the upcoming Virasey-Rubin Observatory, will map the sky in unprecedented detail, tracking billions of galaxies and helping refine our cosmic maps. Beyond the horizon, peering into the unobservable universe. Beyond the observable universe lies an expanse we will likely never directly witness. The cosmic horizon is a limit set by the age of the universe and the speed of light. Light from more distant regions has not had enough time to reach us, making those areas effectively invisible. This horizon is constantly shifting as the universe expands, meaning that with each passing moment, new parts of the cosmos fall out of reach. Despite this, scientific theories and observations suggest that the universe extends far beyond what we can see. The CMB appears remarkably similar in all directions. This suggests that the structure of the universe continues beyond our observational limit. If there were an edge to the universe, we would expect to see anomalies, an abrupt cutoff in galaxy distributions or distortions in the background radiation. Instead, the data suggests that space extends far beyond what we can measure. If the universe is infinite, then it extends forever, containing an endless number of galaxies and stars far beyond our reach. If it is finite but unbounded, space could wrap around itself in a way that is difficult to visualize. In such a scenario, traveling in one direction indefinitely could eventually bring an observer back to their starting point, much like moving on the surface of a sphere. There is the possibility that the physics governing the distant universe might not be the same as what we observe locally. Some theories suggest that regions beyond our horizon could have different fundamental constants or forces. In these distant areas, gravity might behave differently, or the ratio of matter to dark energy could be completely altered. If this is the case, galaxies in these regions may have formed in ways entirely unlike what we see within our observable limits. Some physicists speculate that space might contain distinct domains, each with its own set of physical laws, forming a complex and varied cosmic landscape. Certain theories propose that our universe is not the only one, but one of many, each existing in separate dimensions or parallel realities. These other universes could have their own physics, making them inaccessible to us in every sense. Some models suggest that they could be connected to our own through high-energy events or quantum fluctuations, but as of now, there is no direct evidence for this. If the multiverse is real, it would mean that our universe, even including the parts we cannot observe, is just a tiny fraction of a much larger reality. The universe is expanding at an accelerating rate due to dark energy. As the universe continues to expand, more and more regions will become permanently unreachable. Galaxies that are currently visible will eventually move beyond our ability to observe them, disappearing from view forever. This means that even if the universe is infinite, our observable portion of it is constantly shrinking in a relative sense. If the nature of dark energy changes over time, it could have profound effects on the distant universe. Some models suggest that dark energy could eventually grow so strong that it rips apart galaxies, stars, and even atoms in an event known as the Big Rip. If this were the case, then beyond our observable universe might be a realm of increasingly intense expansion, where matter itself is being torn apart. Other models suggest that dark energy might weaken over time, allowing gravity to reassert itself, potentially leading to a future where distant regions collapse back together. While direct observation of the unobservable universe is impossible, indirect methods may provide clues. If scientists were to find unexpected patterns or anomalies in the CMB, it could hint at structures or forces beyond our observable reach. If something exists beyond what we can ever measure, does it truly exist in a meaningful way? Some argue that only the observable universe is relevant, as anything beyond it has no practical effect on us. Others believe that the unobservable universe is just as real as what we can see, even if we can never directly interact with it. Ancient civilizations speculated about the edges of the world, and early astronomers debated whether the stars had a limit. Today, with advanced telescopes and precise measurements, we have a clearer picture of the cosmos than ever before. Yet even with all our knowledge, we are still faced with the ultimate boundary, the edge of our ability to see. What lies beyond remains one of the greatest mysteries of the universe. Simulating the colossal, supercomputers modeling cosmic immensity. Understanding the vastness of the universe requires more than just telescopes and observations. Many cosmic processes take place over millions or even billions of years, far beyond the timescales of human observation. Others involve forces and interactions so complex that no single equation can capture their behavior. To make sense of these enormous scales and intricate dynamics, scientists turn to supercomputers, machines capable of performing trillions of calculations per second. These computers allow researchers to build detailed models of galaxies, black holes, and even the entire universe, creating digital simulations that reveal how cosmic structures form, evolve, and interact. One of the most ambitious simulations ever created is the Millennium Simulation. Run by the Max Planck Institute for Astrophysics, it modeled the formation of large-scale cosmic structures in incredible detail. By inputting data about the early universe and applying the known laws of physics, scientists created a virtual cosmos spanning billions of light-years. The simulation tracked the movement of over 10 billion virtual particles, representing the distribution of dark matter and its influence on the formation of galaxies. It provided one of the clearest digital reconstructions of how gravity shapes the universe over time, confirming many theoretical predictions about the web-like structure of the cosmos. Another groundbreaking project is the Illustris simulation, which goes even further by modeling not just dark matter but also the behavior of ordinary matter, gas, stars, and black holes. This simulation follows the evolution of the universe from just 12 million years after the Big Bang to the present day, covering a vast cosmic volume. Unlike previous models, Illustris includes realistic physics for how stars form, how black holes grow, and how galaxies interact with their surroundings. It revealed insights into galaxy mergers, the influence of supermassive black holes, and even the distribution of elements across space. Then there is the Eagle Project, which stands for Evolution and Assembly of Galaxies and Their Environments. Unlike Illustris, which primarily focuses on large-scale cosmic structure, Eagle provides a detailed look at the formation and evolution of individual galaxies. It incorporates complex physics, including how stars are born and die, how supernova explosions distribute heavy elements through space, and how supermassive black holes influence their surroundings. The simulation produces galaxies that closely resemble those seen in real observations, giving astronomers a powerful tool for testing their theories. Creating these simulations is not as simple as pressing a button and letting a computer do the work. Scientists must input a vast amount of initial conditions: temperature, density, the ratio of different elements, and the distribution of dark matter. Then, they apply fundamental equations governing gravity, fluid dynamics, and thermonuclear reactions. The computer then calculates how these factors influence each other over time, often taking weeks or months to complete a single simulation. These models must also be checked against real observations to ensure they accurately reflect the universe. When the simulated results match what astronomers see in the sky, it strengthens confidence in our understanding of cosmic physics. By modeling how galaxies move and cluster together, scientists have been able to infer where dark matter must be located and how much of it must exist. Similarly, by simulating the expansion of the universe, researchers have tested different theories about dark energy. These simulations have helped refine estimates of how much dark energy exists and how it influences the fate of the universe. In addition to studying large-scale structures, supercomputers are also used to model extreme environments, such as black holes and neutron stars. Simulating a black hole requires calculations of Einstein's equations of general relativity, which describe how space and time warp under immense gravity. Scientists have used these simulations to understand what happens when two black holes collide, how accretion disks around black holes behave, and what signals we might detect from these events. One of the most exciting applications was in predicting the gravitational waves produced by merging black holes, predictions that were later confirmed when LIGO detected these ripples in space-time for the first time. These simulations also help solve some of the biggest mysteries in astrophysics. One major question is why galaxies have the shapes they do. Simulations suggest that galactic collisions play a major role in shaping these structures. When two galaxies merge, their gravitational interactions disrupt their original forms, sometimes triggering bursts of star formation. By running different collision scenarios, researchers can test which ones best match the galaxies we observe today. Supercomputers also allow scientists to simulate conditions that existed at the very beginning of the universe. The Big Bang left behind a nearly uniform distribution of matter, but tiny variations in density eventually grew into galaxies and clusters. By simulating this early period, researchers can test different ideas about cosmic inflation, the rapid expansion that occurred just moments after the Big Bang. These models have helped explain why the universe appears so uniform on large scales, while still having enough structure to form galaxies and stars. Beyond scientific research, digital recreations of the universe have also become a tool for education and public engagement. Virtual reality and computer graphics allow people to explore the cosmos in ways that were once only possible in science fiction. Programs like Space Engine and Universe Sandbox give users the ability to fly through galaxies, observe planetary orbits, and even simulate the collision of entire star systems. These software programs are built on real astronomical data, blending entertainment with scientific accuracy. They allow people to experience the scale and complexity of the universe in an interactive way, making cosmic exploration more accessible than ever before. With a VR headset, a person can stand on the surface of Mars, fly through the rings of Saturn, or witness the birth of a star up close. These experiences help bridge the gap between raw scientific data and human understanding, making the abstract vastness of space feel more tangible and immediate. Museums and planetariums have begun using these tools to create immersive exhibits, allowing visitors to take virtual journeys across the cosmos without ever leaving the ground. As computing power continues to grow, our best simulations are becoming even more advanced. New projects such as the TNG-50, TNG-100, TNG-300, and the latest TNG cluster simulations model galaxies with unprecedented detail, tracking the movement of gas clouds, the formation of supernovae, and the interactions of black holes with their environments. Future simulations may incorporate quantum mechanics and exotic physics, allowing scientists to explore even more speculative ideas, such as parallel universes or higher dimensions. While no simulation can perfectly recreate reality, these digital experiments have transformed our understanding of the cosmos. They allow scientists to test theories, explore the effects of cosmic forces, and make predictions that can be checked through observation. By simulating the Colossal, we gain a deeper appreciation for the immense complexity of the universe, one that is both vast beyond imagination and intricately connected through the fundamental laws of physics. How does the enormity of these structures make you feel? Leave your comments down below, and if you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.